Hi, everybody, and thanks for joining today's webinar. My name is Ben Sawyer, and I am the webinar host here at Hazelcast. Today, we're going to be looking at Hazelcast JIT. And John Genchaj is the JIT team lead here at Hazelcast, and he's going to be giving us an introduction to Hazelcast JIT. And without further ado, I'm going to go ahead and turn it over to John.
Hello, everybody. So thank you for joining today. So today I'll be talking about Hazelcast JIT, which is a new product from Hazelcast and the first new product, I would say, after our IMDG offering. So to start with, how do we define JIT? JIT is a general purpose distributed data processing engine, which is built on Hazelcast at its core and based on directed acyclic graphs to model the data flow. As I think most people attending would be familiar with Hazelcast, I'm imagining, and Hazelcast is an in-memory data grid, and it's distributed and can be used to store data mainly as a cache, or it can do some lighter weight data processing as well. And so why did we decide to come up with this product? I think, yeah, the main initial reasoning was we wanted to build a distributed JIT stream implementation for Hazelcast data structures. So Hazelcast provides some distributed data structures such as map, and JIT stream is an API that was released with Java 8, which provides methods to basically run different queries within on data structures. And so the distributed JIT stream would be an implementation of this API on top of a Hazelcast map, and it would need to be executed in a distributed way. So one of the options that we looked at was to evaluate what kind of data processing capabilities are currently present in Hazelcast. And some of these are executor service and interprocessor and MapReduce, which is also known as job tracker. But none of these quite fulfill the requirements to implement something like a JIT stream, which is fairly general purpose. And most of the other current execution processing capabilities are limited to certain use cases. And also just generally, Hazelcast is a distributed system, and as such it provides a quite nice foundation for building distributed data processing on top of it. For example, many other products within this big, I would say, data processing space, such as Spark, they rely on other software, for example, things like Zookeeper, to take care of the distributed aspect of the system, whereas Hazelcast provides all of this natively. And of course, another advantage would be that we could unify an IMDG, which is an in-memory data grid. So this is in-memory storage with the advanced data processing capabilities. And this is also another unique proposition. So so just looking at what JIT can do. So it's, as I said before, it's built on IMDG, and it's able to ingest data from many different sources and process this data and possibly enrich it with data from IMDG and then write it either back to IMDG or to another sink. And it can also be used for such as applications such as alerting or analytics. So in terms of the architecture, it's quite a lot of different things here, but I think the main thing to see here is that a lot of the core functionality is based on Hazelcast and is shared with Hazelcast. So things like deployment, networking, cluster management, partition management, even the data storage for things like map and list is based on Hazelcast. And JIT provides a kind of a layer on top of that, which implements the actual data processing execution engine. on top of this core functionality from Hazelcast. And then it also provides some additional connectors to different data sources. I'm sorry, I think I was paused somehow. Sorry about that. Okay, so I was just showing this slide previously, this was basically describing the architecture and the kind of a use case for Hazelcast, how it would fit in an architecture. So you would be ingesting different streams and enriching it through IMDG and then outputting to some other application or back into IMDG. And then in terms of the architecture, we have several things that are dependent on IMDG. So these would be things like deployment, networking, cluster management, partition management, data structures, and the JIT itself provides the execution engine for data processing. So I think if you look at what's actually unique about JIT, it's I think one of the points is it's integrated with Hazelcast, so it can be used as a source or a sink very easily, and also in a very performant way. It's easy to program and easy to deploy. I think this is probably one of the reasons behind this, I think, is because of this philosophy that we have at Hazelcast, that we don't have any dependencies. And just like Hazelcast, JIT is like a very small jar file you can just download, and you can also embed it inside your application. And it has zero dependencies. It has the same cloud features as Hazelcast in terms of discovery on the cloud. And in terms of performance, we have focused a lot on performance, and we do very well here, I think, compared to other frameworks in the space. And also, yeah, we are all developers, and it's made for developers. So in terms of deployment, the story is quite similar to Hazelcast, I would say. So you can run it embedded. So in terms of deployment, you can embed JIT into your application. It's just a single jar, and it can run within the same JVM as your application. So you can even use it to OEM, so you can build some other framework on top of JIT using it as a data processing engine. And of course, you can also run it standalone as a standalone cluster and use it more like a typical client-server application. And also in terms of how you would integrate JIT with Hazelcast, it's also can work in an embedded mode, so you would have one cluster of both Hazelcast and JIT running on the same nodes, and then JIT itself embeds the Hazelcast instance inside it. So that would be one way to do it, and this way you are kind of unifying your computation and storage into the same application. Or you can use it as a separate cluster, so you can have a dedicated in-memory storage cluster and a dedicated computation cluster. So these are kind of different choices that you can make depending on your use case. In terms of performance, so we did a benchmark on running on HDFS, and this is just doing word count, which is a quite simple application, but I think it's quite good for benchmarking because you can't really do much to cheat in terms of optimizations, like specific optimizations for this case, because you have basically a large file with a lot of words in it, and you're counting how many times each word occurs within this file. So this is running on HDFS as a source and as a sink. So we are running this test on 10 nodes with 4 cores each. And if you look at the throughput compared to, these are pretty much the latest versions of Spark and Flink, JIT did very well here, I think. So we are about almost twice as fast as these two other frameworks. And we also did a comparison to fork join pool. So fork join pool is what Java toolstream is implemented on in the JDK. So if you're using Java toolstream, it's using fork join pull internally. And this was just to see how we would compare to something like a very optimized for local operations type of engine. And yeah, first we tried it, and in the first run we were a lot faster. And yeah, we thought this was a bit strange because, I mean, we were not really expecting to beat it because fork join pull is yeah, it's like very optimized for this use case, and something like word count is like a dream scenario for fork join pull. And apparently it's because since it doesn't know the size of the stream, it cannot really parallelize the work, whereas JIT can do this. And so first, if you load the list and then make it like make it the size a known quantity, then it's able to parallelize the work, and then it performs a little bit faster, but not by a lot. And yeah, if you think about it, it doesn't need to deal with anything like partitioning or networking or serialization. I think this is quite a good result for JIT, I would say. So just to go back a little and talk about DAG processing. So initially I mentioned JIT is a DAG processing engine. So I'll just try to explain what that means for those not familiar with this concept. So directed acyclic graphs are and can be used to model computations. Each vertex represents a step in the computation, and it's more or less a generalization of the MapReduce paradigm. So everything you can do with MapReduce, you can do with a DAG-based model. And it can work for both batch and stream processing. And this is a quite well-known paradigm, and there's other frameworks, systems that are using this, such as TES, which was kind of a successor of MapReduce, and Flink and Spark, for example. So previously in MapReduce, you would need to do several MapReduce jobs to do certain operations. You would need to chain them. And in a DAG-based system, you can just represent everything in one graph. So just to go back to the word count problem, where we want to count how many times a word occurs in a given text, let's say. Yeah, what we would do is just iterate through the lines, split the line into words, and then update the running total of counts with each word. So something like this, simplified, where we are just iterating and then updating our hash map, where we store the running totals for each word. And that's it. So there's not much else to do. But of course, the problem with this is it's single-threaded. And if you have a huge amount of data, this will be quite slow. So if you try to model this problem in terms of a graph, we have an input we are which we get the text from, and then we have a tokenizer step which splits the text into words for each word, and then the output is a word. And then we have a reduction step or reducer, which will take this word and update the running totals. And once the input is finished, it will emit whatever the values it holds, and it will go into some output. So this can still be done this way with a single-threaded execution, where we run the first input and then second vertex and the third vertex and so on. So we were just running one thing at a time. So this is still possible to do. To make this run in parallel, we need to introduce concurrent queues. And this way we can, each vertex can do its processing independently, produce output, and this output will be buffered inside the queue for the next vertex to consume. So this way we can run each step independent of each other. And then within each step, we can also parallelize the step into multiple parts. So since we are doing something like word count, each line is pretty much independent from each other. So a tokenizer can process a line independently from another one, which is processing another line. So you can divide your data by lines and then send the lines to different tokenizers, which can do the work. And in the reducing step, for now, you still have, you need to know all the words So you still have one reducer. So the next step is just to make the reducer also partitioned. So when you're sending your input to the tokenizer, you don't really care which one it goes to. You just find one that's maybe not busy or something like that. But when you're looking at when you're sending the words to the reducer, then you need to take special care, because if you have a word, for example, let's say the or something like that, every time you encounter this word, you need to make sure it goes to the same reducer, because otherwise you will have the same word in two places, and then you would need to combine the results again. So to avoid this, you need to partition your data by the word itself. So the only thing that matters is the same word always goes to the same reducer. And then, yeah, the next step is to distribute this work across many nodes. And to achieve this, I've added one more step called combiner. So first we do locally. Of course, this also assumes that your data is partitioned across the nodes as well. So each node has some input, and you're doing the reducing step as before. And in the combining step, you're combining results from different nodes. So each node has one copy of, let's say, the word the with a total, and then all these are being combined in one place. And to achieve this, you need a partitioning scheme where all the nodes agree on which partition is on which node. And as you can imagine, Hazelcast already does this. We have a distributed partitioning scheme within Hazelcast, and this is a quite natural fit for JIT to use the same partitioning scheme. So going back to JIT, JIT core is the main engine, and it provides the low latency, high throughput distributed DAG execution at its heart. And Hazelcast provides the partitioning, discovery, networking, and serialization aspects. So it is running a Hazelcast node embedded inside it, and it's providing some services on top of Hazelcast. And the DAG itself, in the DAG itself, each vertex is represented by something called a processor, which does the main data processing on the node, which is also not thread safe. It does not need to be thread safe. These vertices are connected by edges, and these processors are executed by something called tasklets, which are allocated to threads. So going back to the processor is the main workhorse of the JIT application. Each vertex must have a processor associated with it, and it's just Java code. And what it does is typically take some input, emit some output, and the processor represents a source, sink, or intermediate step as well. And we provide convenience processors for the most common operations like filtering, flat map, and grouping and accumulating. So I have some code here that just shows how you define these vertices, and each vertex can have several processors of the same type. So and this way the work can be parallelized. So each node, in terms of DAG execution, each node in the cluster runs the whole graph, and each vertex is executed by a number of tasklets. So there is one tasklet per processor, and there is a bounded number of execution threads. So this is typically the system processor count. And we also have some work stealing technique between execution threads. So work stealing means, in this context, if a thread has more work to do than some other thread, they kind of balance the work between each other. So one of the threads steals work from another thread. And we have also a system for ensuring back pressure between vertices. So if a vertex, if the processors of one vertex is kind of, let's say, consuming input slower than is being produced, the producers will slow down, and this will give more room to the consumers to execute their logic. And the whole idea behind this is something called cooperative multi-threading. And this is also, could be said, is similar to things like green threads. So it's not operating system level threads, but more like little tasks that can be run in succession. So we have one native thread which can run thousands of these small tasklets without any overhead or very little overhead. And also we guarantee core affinity, which means we get more cache hits. So this gives really good performance. And each tasklet does a very little amount of work each time. So this is less than a millisecond typically. And one of the requirements is that these tasklets must be non-blocking. And if there is no work for its operating system thread, none of the tasklets have any work to do, then it will back off, and this will just ensure that we don't do busy waiting. And in terms of edges between vertices, this is implemented using lock-free single producer, single consumer queues. These are also known as ring buffers. And we use wait-free algorithms on both sides, and we avoid volatile writes using things like lazy set, so all the buffer can be flashed at once in an efficient way. And we do, since we have this bounded queues, the load balancing is quite a natural outcome of this. So if the queue is full, you cannot put more things into it, and then you'll have to back off. And it's also not completely, I mean, this requirement for non-blocking is not completely avoidable. So because sometimes you have to deal with file I/O or network I/O. And in this case, we also support non-cooperative processors. And these have a dedicated operating system thread to it, and they don't really need to, there is no real rules around this. They can do pretty much whatever they want. And this is mainly used for sources and things when you're reading from a file, writing to network, and such things. In terms of how an execution happens, so for example, you would have a producer vertex and a consumer vertex, and you might have 4 instances of the producer and 2 instances of the consumer. And so there will be a queue between each producer and consumer pair, and the producer will decide which consumer it will send the output to. So this can depend on different things. It can depend on if the consumer is already, maybe its buffer is already full, you cannot put more things into it, or you are using something like partitioning where you want to go, you have to send it to a specific consumer, and these are defined by the edges properties. And in terms of the tasklets, they will just get mapped to 2 threads. If you have 2 threads in your system, 2 execution threads, then they will be distributed among these 2 threads. So in terms of the edges, we support something called Uniqueness, which means you just pick any downstream processor. And this is typically when you're reading from a source, and then you want to do maybe some more operations on it. Then you don't really care which processor it goes to. And there's broadcast, which the output is sent to all downstream processors, and this is typically used for enrichment. Like you have some static data which you want to join to your streaming data. So you want to enrich your streaming data with some static data, and then you want the static data to be available in each processor. This way you can have very fast lookups. And partitioned edge is typically used when you want to distribute the data based on some key, where you want to ensure the items with the same key end up in the same place. And vertices can also have more than one input, and this allows things like joins and cogroup. Vertices can have more than one output. This enables things like splits, where you split the data into 2. And edges can be local or distributed. A local edge means data stays within the same node, and the distributed edge means the data can travel across the network, which has obviously higher cost because it will be distributed to other nodes as well. And in terms of input and output, we currently have readers and writers for Hazelcast IMAP and iList, and soon iCache, HDFS, Kafka, and some basic socket with text encoding and file reading and writing. And we also have the API, processor API, where you can implement your own logic. In terms of the APIs, so the DAG API itself is powerful, and but it's kind of low level, and it describes how vertices are connected to each other in a very verbose way, I would say. So you define vertex by vertex how you want your execution to look, and then you define your edges and how these edges should be connected to each other, and then you can run your job based on that. So this is kind of the core API, and I would say the most powerful API we have. So the heart of this API, we have the processor itself, and this provides a unified API for sinks, sources, and intermediate steps. Each processor has an inbox and outbox, and this what it does is typically consume the inbox and put some items into the outbox. If it's a source, it will not have an inbox. It will just put things into the outbox, and if it's a sink, it will be the other way around. So it will not have an outbox, but it will just consume things from the inbox and write them somewhere. And the main two methods to implement is the try process method. So this basically just process an incoming item, and then optionally it can populate the outbox. And the complete method is called after all input has been consumed. So this is typically used in batch scenarios where you're accumulating some data until the input is finished completely, and then you're going to do something. And there's some differences in the API. For example, you might have noticed in these calls we have a Boolean return value, and this kind of indicates if you are yielding or not. For example, you might need to put something in the outbox, but there might not be any space, and then you have to yield if you have a cooperative processor. So you need to respect the outbox and yield. So you have to. This makes it slightly trickier to code these, because you cannot just do like simple logic. You have to kind of pick up where you left off. And but yeah, the benefit is we can have really good performance. And if you have a non-cooperative processor, then you're kind of free to do whatever within these methods. You can block indefinitely without any side effects. And another API that we have is the distributed JIT stream. And the JIT stream is something that was introduced with JDK 8. And we have added a distributed JIT stream support for Hazelcast map and list. So what this basically means is you can run pretty much all JIT stream operations on a Hazelcast map, and this will do a conversion into a JET tag. So there's a query execution engine that will convert the JIT stream into a tag and execute it. And there's a slight, there has been slight complication with lambdas, but because JIT stream itself uses things like function and predicate from JDK, and none of these interfaces are marked as serializable. So we had to do some tricks to get it working, but I think it works quite smoothly. So just wrapping up the different APIs we have. The processor API itself is quite low level and powerful, and basically you can do any kind of computation on it. JIT stream API is kind of familiar, but it has a bit limited functionality. And pretty much all data processing frameworks have their own API. And there has been some attempts at unification. For example, cascading is one which was based off MapReduce originally, so you could express your MapReduce query in a more I would say, user-friendly way on a higher level. And there's also something called Apache Beam, which is originally coming from Google, based on their Google Cloud data flow. But I think in reality, these unification attempts have not proven to be major successes. I think simply because people don't typically like write some high-level query and then execute it on different engines. I think the decisions are kind of made before that on which framework to use and so on. And I think none of these have been very user-friendly either. So in terms of supporting these APIs, we looked at cascading initially, and we did a prototype. And this was, I think, more of a way for us to prove to ourselves that we can support any computation that can be done via cascading, which is a quite powerful language. And now I want to do a demo. Okay, so I have a word count example here, which is from our code samples repository. So you can actually find this on GitHub in the Hazelcast JIT code samples repository. And what it does is we have the books here, which are downloaded from Project Gutenberg. It's just a couple of books, I think. Yeah, it's more than a couple, but so these are different books in English language. And what we are doing is we want to find the most used words within these files. So, and to do this, we are first loading all the books into memory, into a map, Hazelcast map. And then we are running a Java util stream query here. Just find this here, zoom in a bit. So this is looks like an ordinary Java util stream code, and we have a special collector that will write the output to IMAP, and then we are just printing out the results. So it's just going to fire up two JIT nodes, and they're going to form a cluster. For now, it's just running on my laptop, both of these. And yeah, as you can see, the results are not majorly surprising. Things like the and of to is the most commonly used words. And I have the same example, which is using the core API. And as you can see, we are building the DAG here, and this is more verbose because, again, we are building each vertex line by vertex by vertex. So this is not a very high level language for describing, but I think the advantage here is you kind of control every aspect of the execution, and you can really optimize things and as you would like. So yeah, we are building the vertices first, and then we are building the edges between them. So I will run this as well, and it should give the same results as the other one. Yeah, as expected, we got same results as the output. So what do we have now, and what's our plans for the future? So the current version of JET is the 0.3.1. So yeah, intentionally we have named these releases with 0 point in the beginning because yeah, we don't see this as the kind of finished product. We are still doing releases frequently, so every 2 months I would say we are doing a new release and adding new features all the time. So one of the things we currently have is the distributed computation engine, JIT stream support, the low-level API, and then all the things that are already provided by Hazelcast, such as discovery, the networking, and the data structures. We have some basic fault detection, so if we detect a failure in any of the nodes, we can stop the whole computation on all the nodes, or if a node leaves the cluster, we can cancel the computation. And we have the back pressure support, which works both locally and also over the network between the nodes. And we have connectors for IMDG and various other things like Kafka and HDFS. So in terms of the future roadmap, we are the next release, we are adding windowing support. So for now, you can still work with streaming sources, but there is no built-in windowing implementation within JIT. You can, of course, build your own using the processors, but we are going to have a much more extensive solution to this, which you can use. And also things like guarantees for message processing, which are currently we don't have. So we have only at most once, but we are aiming for a choice between at least once and exactly once in the future. And in this aspect, you have some performance trade-off. Of course, if you want exactly once, it's more expensive than at least once. And then we are doing more integrations into Hazelcast. We are adding JCache, and we are going to add projection support and predicate support when you're reading from map. And this way you can make use of Hazelcast indices. And also we are going to add, currently the map reader works by just reading whatever is in the map. But if you're updating or adding new items, these are not reflected. So we are going to be adding support for streaming changes to the map. So you can build a streaming application using map as a source. And then there's management functionality. One second. Sorry, just lost my voice there. We are adding management functionality such as monitoring and visualizing the DAG, and more connectors, and also support for things like Cloud Foundry, which Hazelcast already supports, but we are going to add JIT support for that as well. So yeah, we have 3.1 or 0.3.1 out, and 0.4 is coming within the next few months. And as you might have noticed, I was using a lot of Java 8 code, and that's because JIT is based off JDK 8 as a minimum requirement, which allows us to be quite Lambda friendly. So any questions? Okay, so I will have some questions here from Mukul Panwar. So one of the questions is, do we need to load data in memory before processing? So yeah, this is a good question. JIT works in both cases, so you can read directly from file. So if you have, for example, Hadoop cluster, your data might be too big to fit in memory. And then, you can just read directly from HDFS. And also you can load your data into a map, for example, and then just process it from there. So both are supported. Another question is, what should be the size of cluster to make it fast processing? Again, I think JIT, in terms of requirement, is very humble. I mean, you can run it even on a very small heap because, what we have is basically a very small jar. So there's no real minimum requirements, I would say. It just depends on what you are doing and what you want to achieve. And then another question, if JIT is running independently as client and connected with Hazelcast IMDG, sorry, this third question, I don't quite understand the question. Mukul, could you repeat it? I think it looks like it's truncated. And then I have a question from Dennis, where he says it's not clear about distributed reducers. Yes, so the distributed group by, it can work out of the box. It's just the way you do your wiring, so how you wire the DAG together. So if you are using, for example, Java Toolstream API, it will do this for you. So for example, I'll just go back to my example here. So in the word count example, so we have the tokenizing vertex, and then we have the reducing vertex and the combining vertex. So the difference here is that you can see that the edge between the reducing and combine is a distributed edge. So we are achieving this two-stage reduction by first doing a local reduction and then a distributed reduction. So yeah, I mean, if you're doing the DAG by hand, then yeah, you can achieve this. If you are using Java Toolstream, then it automatically always tries to do a distributed reduction using two steps automatically. Okay, is there any more questions? I think there was one question which from Mukul, the last question you had. If you could repeat that, that would be great. And yeah, I will just show that we have the homepage here, and I will recommend to we have the reference menu here, which has quite in-depth documentation, and you can just there's also sort of about word count here as well, which you can walk through, and a lot more information about the API. And we also have the code samples, which you can find 3.1 code samples with Hadoop and Core API. So there's different things here which you can just play around if you want to get a more feel for how JIT works. So okay, there's one more question from Manish. Can JIT work on top of existing Hazelcast map 3.6? So currently we only support 3.8 as the minimum Hazelcast version. So you will need to upgrade to 3.8 to use JIT. Okay, I think there's not any more questions. So yeah, thank you everybody for attending.
Thanks, John. Thanks everybody for attending, and there will be a recording of this webinar, and we'll post it up with slides and a video, and we'll send an email out to everyone who registered. So you should expect that in the next few days, and you can feel free to, of course, forward that, share with anybody else who might be interested. And hope everyone has a good day.